So let's look at how to name molecules with chirality centers, or as I've written here, chiral centers, you'll also hear them referred to as stereogenic centers. They've got lots of names, they're important. So one thing to remember is that most of the name of our stereoisomers is the same. We have 3-methylhexane, and 3-methylhexane over here. The only thing that's different is this little letter in the front, and this tells us which enantiomer we are talking about. So we designated enantiomers using R or S, as we just saw, and the rules that we use for this are called the Cahn-Ingold-Prelog rules for priority, and we do use these for a couple of different things. The rule that you run into first and that you use the most is if the atom of the highest atomic number attached to the stereocenter gets the highest priority. And if then you have two identical atoms, then you need to go to the next atom until you see a difference in order to figure it out. So, for example, bromine down here has the highest priority, so it gets 1 because it has the highest atomic number. The lowest atomic number belongs to hydrogen, and so that's going to be the lowest priority. Should give the number 4. And then we have to figure out ethyl versus methyl, and it might be intuitive that, oh, the ethyl is a bigger group, so therefore it should have higher priority over the methyl. And it turns out that that will actually give you the wrong answer sometimes. You want to do it by first looking at the first carbon and comparing that carbon here. So those are the same, so that doesn't help us. Since those are tied, we have to move to the next atom. Since we have 3 hydrogens here and 2 hydrogens here, that doesn't help us yet. But look, the next carbon here is the next atom here is a carbon. That's different and higher priority than one of those hydrogens. And so the ethyl group gets the higher priority. And so that's 2. And then the methyl is 3. There's some other rules here that are similar. This rule is similar. Tritium, it has a higher mass number than deuterium, higher mass number than hydrogen. And so the priority is 1, 2, and 3, as you can see there. And so priority goes to the higher mass number, which I think is probably intuitive. So one of the things that we do run into a lot more often than the isotope question is what to do about multiple bonds. And this is the weirdest one. Just in your head, if you see a double bond to a carbon, it's like this carbon here was bonded to 2 carbons, and this carbon is bonded to 2 carbons. We're not doing any reactions. We're not doing anything with this. It's just not doing anything real with it. It's just a rule to help us figure out relative priority. And so, for instance, a carbonyl, you have the carbon doubly bonded to the oxygen. That's like this carbon is actually bonded to 2 oxygens. So we can see that rule coming into play in this example on the left, where it's like this carbon is actually bonded to 2 other carbons, or pardon me, to 2 other oxygens. That's what that rule tells us to pretend. And since this carbon is bonded to 2 other oxygens, that has higher priority than an oxygen and a hydrogen. So this is actually the first priority. This, I should point out, this is our stereocenter over here. It's the carbon bonded to 4 different things. The oxygen here has highest priority, and then we have the hydroxide, and the methyl group comes 3rd. And what we can't see going back is there is a hydrogen back there, and that would have priority. It's not that we can't see it, it's just not drawn. So it's going to the back, and that has the 4th priority. So similarly, on the example to the right, let's see here, we have our stereocenter right here. Highest priority goes to the OH group, then the CH2OH, because oxygen is higher priority than carbon. And then we have our ethyl group. And again, we have a an H going to the back. Okay, so then the next step would be to place the lowest priority group to the back, and then kind of pretend that you're driving, like you have a steering wheel. And if you turn your steering wheel to the right to go from priority 1 to priority 2 to priority 3, then that's R isomer. And if you go counterclockwise, then that's the S isomer. So if we go back to our previous example, we're actually in the right orientation for both of these. We'll have to, you can kind of change the orientation and redraw it, or use a model to change the orientation if what's given to you isn't in the correct orientation. You can also, if like the hydrogen was going to the front, you could also just figure out whatever configuration you have and then flip it over. So if you got R, you would say it was S. And we can look at that in class more. In any case, these are going in the correct direction that hydrogen is going back. So we go from 1 to 2 to 3. So that's going S counterclockwise. And similarly over here, we go 1 to 2 to 3. And again, is counterclockwise. So that again is S.